Hello BTech DT. Today's topic of lecture is drying principle, methods and applications. Now, first is introduction. Drying and dehydration of fruits and vegetables is an age-old method to preserve these products for extended shelf life. Removal of the water, that is 75 to 90% present in fresh commodity, results in reduction in the water activity and ultimately resistance against most of the deteriorative agents. The removal of water is carried out by the application of heat, and this heat is usually supplied in the form of solar energy or artificially generated hot air. Removal of moisture and exposure of heat often results in poor textural attributes, loss in nutritive values, that is, loss of vitamins, discoloration, and loss of flavoring compounds. Although both drying and dehydration are interchangeably used, drying is referred to removal of water to an equilibrium moisture content, while dehydration is removal of water to an almost bone dry condition. So, first is drying and dehydration. Both are same in the technique as they both are removal of moisture. It may be sun drying, then it will not control the external atmosphere, but it will utilize heat to remove the water. But in dehydration, because it is done by artificial environment, whether it is hot air or osmotic dehydration or freeze dehydration, so it creates the artificial environment. Now, drying is the simple removal of water to an equilibrium moisture content. Now, what is the equilibrium moisture content? We know that everything that is live, that do respire, wants to make or tends to make equilibrium with the environment, with its environment. Means if tomato is there, if one tomato is there and above 90% moisture content is in it, it will try to equilibrate it with its environment, the outside air. So whatever the moisture content of the outside air, it will try to make equilibrium with it to be equal to it. Means if tomato has higher moisture content than air, then the moisture will leached out to the air to maintain the equilibrium. If the moisture content of air is higher than tomato, then tomato will receive the water and will become soggy. So, equilibrium is the state where no exchange of moisture is there, because they have equal moisture content, the product and the outside of air. So now, what is water activity and reduction in water activity? how reduction in water activity accelerate or makes resistance against most of the deteriorative agents. Now, what are the deteriorative agent? Naturally, the metabolic process, the continuation of high metabolic process is one deteriorative agent, because if oxygen is taken in the system at higher rate, there will be metabolic activities. And what do metabolism does? It deteriorate or disintegrate macromolecules into micromolecules, which will affect the fruits and vegetables raw texture, and it will deteriorate its quality. Now, second is the microbial load. The second deteriorative agent is the microbial load. So, the microbes present within the food system, whether it is fruit or vegetable, they use the free water for their mobilization purpose. For the mobilization of nutrients they take from the food, and the metabolic waste, the movement of metabolic waste from the microbes to the cell is facilitated by the free water available within the food system. So, reduction in the water activity means the unavailability of free water for microorganism. So, this will restrict the growth of microorganisms. Now, why we do drying of food? First is, water activity is defined as the ratio of vapor pressure of food to that of vapor pressure of pure water at a constant temperature. Now, what is the vapor pressure of the food? Because of the metabolic activity, there will be heat generation and heat generation will tend to evaporate the moisture content that is freely available within the cell system, and the release of this vapor creates vapor pressure on the cell and out on the food system. So, water activity is the ratio of vapor pressure of the food, and it is compared to vapor pressure of pure water. Now, reduction in water activity controls the chemical as well as microbial changes, as we have already discussed. Now, reduction in weight, size and volume of the material, because fruits and vegetables have 80 to 90% or even 99% of water as composition, then the reduction in the moisture content, that is 75 to 80% of the reduction in water content, will reduce the weight, size and volume of the food material. Hence, bulk transportation becomes easier and cheaper. Packaging requirements are simple and cheap, because there is no need to design the food packaging, because there is no low water activity or lowest water activity. So, the chemical reactions as well as microbial changes are almost inactivated. Now, facilitate further processing. To facilitate further processing, like grain drying for flour. So, And for fruits and vegetables, the dried products are used as intermediate products in the food factories. Now moving to the next, that is water content in food. As we have already discussed, water present in food in two forms. First is free water and second is bound water. What is bound water? Which have lower vapor pressure, lower mobility and greatly reduced freezing point. Why is it so? Because it is bound to the molecules or the solid particles like fiber. So this water is unavailable for further chemical reactions or microbes. Now this is the table. There is a table. Table heading is water activity as affected by the extent of bound water. Now extent of bound water, that is tightly bound water which have water activity more than 0.3. So it is mostly unavailable for the chemical reactions and microbial reactions. Now moderately bound water has water activity of 0.3 to 0.7. Then loosely bound water, it has water activity more than 0.7% and free water has water activity of 1. So 1 ratio ratio between the specific food, vapor pressure of the specific food to the true pure water. If it is 1, this is the maximum water activity, and if it is less than 1, there is reduced water activity. Now, mechanism of drying. When hot air is blown over a wet food, heat is transferred to the surface and latent heat of vaporization causes water to evaporate. Water vapors diffuse through a boundary film of air and is carried away by the moving air. This creates a region of lower water vapor pressure gradient is established from the moist interior of the food to the dried air. The gradient provides the driving force for water removal of the food. This we can understand by seeing the schematic diagram of movement of moisture in the interstitial spaces of food cells during drying in fruits and vegetables. Now we can see that this is the cell system. Then this is the capillary space within the red lines are the capillary space which have free water in it. The dotted line is the feed surface, and from this surface hot air is moving in this direction. When hot air moves at the surface of the food, free water moves towards the direction of the moving air. So, what is the driving force? Driving force is the water vapor diffused through the boundary film of air and is carried away by the moving air. So whatever free water that diffuses through this boundary film to the direction of air Because of the latent heat of vaporization, by the latent heat of vaporization as an effect of heat, then this creates a region of low water vapor pressure within the cell system, because we have already discussed that whatever water evaporates during the metabolic activity from the cell, it is there as free water in between the cells. So water vapor pressure, and it exerts the vapor pressure within the system. So when the water moves towards the direction of the moving air, it reduces the water vapor pressure. So lower water vapor pressure gradient is established from the moist interior of the food to the dry air. This gradient provides the driving force, because we know that everything in any state wants to move from higher concentration to lower concentration, whether it is a liquid or whether it is gas molecule. So because there is higher moisture content within the food system and lower moisture content outside the food system, because of the hot air movement, the gradient established and the movement of moisture content into the form of vapor becomes the driving force. This gradient becomes the driving force for the removal of water from the food. Now, how the movement of water, the free water in between the cell, moves towards the movement of air because of the capillary force, because there is a capillary force in between the cells. Now, diffusion of liquids caused by concentration gradient. Now, because the highest concentration is within the cell, we know, then lower concentration is in between the cell. Now lowest concentration is outside the cell, we know. Okay, now diffusion of liquid caused by concentration gradient. What is concentration gradient? The tendency to move towards higher concentration to lower concentration. So when the movement of moisture is what moisture? That is present in between the cells, move towards the direction of air, then tendency or the concentration gradient start diffusion of liquid from the cells which has higher concentration. Movement of liquid starts to diffuse within the cell to the intercellular space. Now, diffusion of liquid which are absorbed in layers at the surface of the solid components of food. So it starts its journey towards the surface of the food and the object is to go out from the system. Now fourth is water vapor diffusion in air spaces within the food caused by vapor pressure gradient. So we have understand that from the cell, if the free water moves through the capillary effect, moves outside the cell system, then within the cell system the moisture content will starts to release into the air spaces within the cell structure, that is intercellular space. And because of the movement of free water through capillary force, this air space is created. Now phase of drying. There are three phases of drying, that is first initial warm up period, second constant rate drying period, and third is falling rate period. Now in hygroscopic food material, more than one falling rate occurs. In first period, plane of evaporation moves inside the food and water diffuses through the dry solid to the drying air. It ends when plane of evaporation reaches to the center of food and the partial pressure of water falls below the saturated water vapor pressure. The second falling rate period occurs when the partial pressure of water is below the saturated vapor pressure, then and the drying is by desorption. Falling rate period is the longest period during drying of food product. EMC, that is equilibrium moisture content, occur when dry spots develop at the surface, so less area exposed to the dry air and evaporation decreases. So when it is the moisture content reaches to the equilibrium moisture content, when there is equal amount of moisture is there within the food and the outside air, it is the condition of equilibrium moisture content. And physically we can make out that equilibrium moisture content is achieved when dry spots develop at the surface, and if dry spots develops at the surface, less surface area will be exposed to dry air and evaporation decreases. Now we can understand the three periods, three phases through this schematic diagram. Now this is the schematic diagram of change in moisture content with time. It is also known as the drying rate. Now we can see that y-axis has moisture content and x-axis as the time. Whatever time it takes to dry the or lower the moisture content. Now we can see that A to B is warming up time. And what is warming up time? We can see that there is increase in moisture content within this time, and B to C, the moisture content is constant. That's why it is known as constant rate drying period. Now C to D, first falling rate drying period, because we can clearly see the clear fall in the moisture content, and D to E is the second falling rate drying period, where the lowering of the moisture content, the speed of lowering of moisture content is less than the first falling rate drying period. Now A to B, how it increases when we are doing drying, then water vapor is releasing from the system, food system, and it is releasing into the air, which is hot and dry. Then why the increase in the moisture content of the food system, as we have earlier discussed that this will create concentration gradient, and moisture bound within the cells will release, and it will create the increase in initial moisture content of the food because of the rupture of the cells. Now to the falling rate periods. So we can understand this paragraph: in hygroscopic food material, more than one falling rate period occurs. In first period, evaporation moves inside the food and water diffuses to dry solid to the drying air. We had understand this. Then it ends when evaporation reaches to the center of food, when the water present in the center of the food start vaporizing, the partial pressure of water falls below the saturated water vapor pressure. Second falling rate period occurs when partial pressure of water is below the saturated vapor pressure. So means the tightly bound water is only present during the second falling rate period. So this is the falling rate period is the longest period during the drying. Now there are four resistance to heat transfer in drying. First is resistance to external heat transfer, resistance to internal heat transfer, resistance to external mass transfer, and resistance to internal mass transfer. So first is the resistance which surface creates, the surface of the food creates for the external heat transfer, that is the transfer of water vapor through the capillary force. Then resistance to internal heat transfer means the water present within the cell, the release of water present within the cell to the intercellular space is the resistance to internal heat transfer. Then resistance to external mass transfer, because of the water vapor transfer, the mass, the cell structure start to disrupt and release the water bound to it. So there is resistance to external mass transfer, the leaching out of vitamins, whatever whatever solute has volatility, higher volatility will start vaporizing with the water vapors. And lastly, the resistance to internal mass transfer, that is from within the cell. From within the cell, the solute starts transferring to the intercellular spaces. So we know that these are the four resistance which come over during drying. Now, drying time. Drying time is the total time required for the removal of water from food material. Drying time during constant rate period is inversely proportional to wet bulb depression, means the reduction in the moisture content of the air, and while drying rate is directly proportional to the wet bulb depression. So now we can understand this by this formula, where drying time is equal to, in bracket, Wi, that is initial moisture content, Wt, that is moisture content at time t, and rho s, that is the bulk density of solid, and L, capital L, is latent heat of vapor, and small d is the thickness of material, small h is the surface heat transfer coefficient, Ta is the dry bulb temperature of hot air. So dry bulb is the temperature of the hot air, and Tw, wet bulb temperature of the air, means the moisture content that is present in the air. So the temperature of that moisture content is the wet bulb temperature, and Ta minus Tw will be the wet bulb depression, the depression of the moisture content which was present in the drying air. So now if velocity of air is increased, h, that is the surface heat transfer coefficient, will increase and drying time is decrease. So if the velocity of hot air is increased, the surface area will enhance the drying rate, so drying time will be reduced. So we can understand the relation, that is drying time during constant rate period is inversely proportional to wet bulb depression, while drying rate is directly proportional to the wet bulb depression. Now, total drying time is the time required to attain critical moisture content. Now, Wc is the critical moisture content. Drying time during falling rate period is decided predominantly by, sorry, one by is more there, so no need of by. Drying time during falling rate period is decided predominantly by diffusion, and so some extent by the capillary action. So drying time due to diffusion is equal to 4d square upon pi square d, that is capital D. First was small d. I repeat the formula: 4 small d square upon pi square capital D, then ln. There are two brackets. First is 8 by pi square, and in second bracket Wc minus We upon W minus We. What is We? We is the equilibrium moisture content. Now this is the drying time due to capillary action, and capital D is the liquid diffusibility from the cells. Now we can understand, if Wi, that is initial moisture content, is less than Wc, that is it is falling rate period. When Wi, that is initial moisture content, is more than Wc, that is critical moisture content.